For the introduction, scheduling means planning tasks or activities in a certain order and time. It is important because good scheduling helps one to use their time and resources efficiently and avoid conflicts. In university, subject scheduling means assigning courses to specific time slots while considering limited resources like lecturers and classrooms. As the number of courses increases, timetable optimization becomes important to ensure that schedules are efficient, practical, and free from clashes. The university offers multiple modules within a number of time slots. Problems happen when modules that share students or resources are scheduled at the same time. It will cause conflicts. Since only one module can be assigned to each time slot, manual scheduling may lead to class clashes and wasted time. Therefore, a systematic and optimization-based method is needed to produce a conflict-free timetable. The objectives of this study are to assign 15 conflicting courses to available time slots without clashes, secondly, to avoid scheduling conflicts between modules, and lastly, to minimize unused and redundant time slots through optimization techniques.
Hello, my name is MAIZATUL and I will explain on the data preparation. For this project, we use a dataset from the Kaggle website. The dataset contains information related to university modules and their scheduled class times. This data is relevant because it allows us to study timetable conflicts and apply optimization methods to generate a non-conflict schedule. First, I will explain Table 1. Table 1 presents the original module scheduling data. Each row represents a module with its assigned date and time. From this table, we can observe that some modules are scheduled in the same time slot. This situation creates conflicts because a student cannot attend more than one module at the same time. Next, based on Table 1, we construct Table 2, which name module scheduling by time slot. In this table, time slots are labeled as S1, S2, S3, and so on. Modules that are assigned to the same time slot are grouped together. When a time slot contains more than one module, it indicates a conflict between those modules. Table 2 is then used to construct the adjacency matrix.
My name is NURUL and NABEEHA binti MUSTAFFA, and in this section, I will explain how the scheduling problem is modeled using an adjacency matrix and how a conflict graph can be derived from this matrix. The adjacency matrix represents the relationship between modules and time slot, where the rows correspond to modules and columns correspond to time slot. An entry of 1 indicates that a module can be scheduled in a particular time slot, while an entry of 0 indicates that the time slot is not available for that module. From this matrix, potential conflicts can be identified by examining each time slot column. If more than one module has a value of 1 in the same column, then this module may conflict if scheduled simultaneously. For example, in time slot 1, both module 5 and module 14 have a value of 1. This indicates a potential conflict if both modules can be scheduled at the same time. In contrast, time slot 15 has only one module with a value of 1, and therefore no conflict exists in that slot. Next, we look at the conflict graph, which is derived from the adjacency matrix. In this graph, each vertex represents a module and an edge is drawn between two vertices if the corresponding module share at least one time slot in the adjacency matrix. Essentially, the conflict graph shows potential scheduling clashes. If two connected modules are assigned to the same time slot, a conflict will occur. From the conflict graph, we can observe these following conflicts. Module 1 and Module 15 clashing on time slot 2, Module 2 and Module 11 clashing on time slot 4, Module 3 and Module 7 clashing on time slot 7, Module 5 and Module 14 clashing on time slot 1 and time slot 6, Module 6 and Module 8 clashing on time slot 3 and time slot 8, and Module 9 and Module 12 clashing on time slot 5.
The figure shows an optimized perfect matching using a bipartite graph for a university scheduling problem. The purpose of this model is to assign each module to one suitable time slot without any scheduling conflict. In this graph, the nodes are divided into two groups. The left side represents the module from MOD01 to MOD15. The right side represents the available time slot from S1 to S15. Connection or edges are only drawn between modules and time slot. These edges show which time slot are possible for each module. Each edge has a cost value. This cost represents how suitable a time slot is for a module. A lower cost means the time slot is more suitable or more efficient for that module. The optimization process selects the best combination of assignment by minimizing the total cost. The matching shown in this figure is a perfect matching. This means every module is assigned to exactly one time slot, and each time slot is used by only one module. There are no overlaps and no clashes. This table shows the final timetable for all modules based on the available time slot. The table presents how module M1 to M15 are assigned to time slot S1 to S15. Each module is placed in a unique time slot, so there are no overlap or scheduling conflict. This arrangement ensures that all classes can run smoothly and students are able to attend every module without clashes. The distribution of module is balanced and follows a one-to-one assignment, meaning each time slot is used by only one module. By using all the available time slots efficiently, the timetable makes better use of resources such as lecture hall and lecturers. Overall, the final timetable is clear, well organized, and support effective academic planning. This table shows the final timetable for all modules based on the available time slot. The table presents how module M1 to M15 are assigned to time slot S1 to S15. Each module is placed in a unique time slot, so there are no overlap or scheduling conflict. This arrangement ensures that all classes can run smoothly and students are able to attend every module with.
In conclusion, this study successfully created a timetable for 15 courses without any clashes. Every course was matched to a time slot like a perfect matching in graph theory. Using optimization techniques, it makes the timetable more efficient, save time, and reduce mistakes. Overall, optimization helps organize tasks well and can be used for other scheduling problems too.